See my screen? Okay,
Yes,
sounds
we
good.
can.
Okay. Hi, my name is Zinal Patel, and I work in Dr. Grover's lab under bioengineering, and I'll be talking about my research related to creating a low-cost pneumatic controller for light compression devices. So, if you've ever been in a hospital or in a medical setting, you've probably seen or may have heard of one of these devices. They're called IPCs, or intermittent pneumatic compression devices. And they're essentially a sleeve that you wear on your legs or arms or anywhere on your limbs where you need to promote blood circulation. They're relatively simple devices. All they do is they compress your limb at certain points in an oscillatory fashion, and they promote blood circulation. They're especially used for patients with diabetes, DVT, high blood pressure, and other medical conditions, as well as for people who are just coming out of surgery and we need to promote blood circulation. However, one of the big problems is that the control system that controls these IPC devices is pretty expensive. On my screen, you can see that the Kendall SCD 700 series goes upwards of $2,000, which is crazy expensive for something that is a critical life-saving device. The sleeve itself isn't expensive, but the control system is expensive and it's bulky. And I think I have a way to kind of reduce that and make it more accessible. So, like I've talked about, these IPC devices are expensive, bulky, and inaccessible. So what can we do about that? Well, my solution is basically creating an air-powered control system to reduce the electromechanical hardware. Essentially, I would be using air instead of electricity, and replacing all of those electrical components and boiling it down to air-powered components that would basically make the device less bulky and more portable, more accessible. So let me break this down a little bit. Basically, I would be doing this through a microfluidics system that's powered by pneumatic logic. Now, it's a lot of words, but what I'm trying to convey is that I would be using microfluidics, which is essentially devices that are powered by either fluids or air that are flowing through microchannels. So with these microfluidic devices, the device that I've been researching and sort of developing in lab is made of two pieces of acrylic with a silicone polymer sandwiched in between called PDMS. And these microfluidic devices, they contain features such as channels, inlets, valves, vents, and outlets, which are all just etched onto the acrylic, and they allow for air or fluid to flow through. In my device and in Grover's lab, we've been researching how to use vacuum to flow through this device. And the reason that we're trying to use vacuum instead of positive pressure or pushing air through it is because then we can implement what is called a monolithic membrane valve. And these are normally closed and they store memory. So kind of just to give like an analogy, imagine that you are on you're on a path. This path is a channel, and you're approaching a door that is a pull to open door. With this pull to open door is similar to a valve. When I don't have vacuum applied to this channel, this path, then the door will stay closed. And that allows us to store memory. That allows us to basically remember its sort of last position. But when I apply vacuum, I can pull this door open, and then I can just create a series of events and open and close gates and valves, and basically create what is like a microcomputer on this piece of plastic. And so using vacuum to power this microfluidic device is kind of the basis for my research behind creating a low-cost IPC. However, one big disadvantage is that when we use vacuum, there's less force and less power that's outputted compared to using air or regular pressure to power this. And so a second part of my research is basically creating these pneumatic level shifters. And so this entire system is analogous to electrical systems, with the channels being similar to wires, with the valves being similar to transistors. And this is essentially a very simple 3D printed device that basically takes sort of the patterns that I output through my vacuum microfluidic chip and converts them into the similar patterns in pressure. And I know there's a lot going on the screen, but essentially when I turn on a vacuum through a tubing that's connected to the input, then this bellow, which is this plastic plastic piece in the middle of this pneumatic level shifter will compress, and that will basically allow pressure to flow through the tubing on the bottom. And so essentially, I'm just trying to translate the logic through and allow myself to be able to use a microfluidic chip that's powered by vacuum, but convey those sort of signals into pressure logic, and use the power of pressure. And I'll summarize this sort of at the end to kind of give you guys a big overarching summary. So a little bit of the materials and methods of how do I create the microfluidics chips. First, I basically designed this on Adobe Illustrator and any sort of vector graphics program. This right here is the oscillator chip that is basically sort of simulating the oscillations that a compression sleeve would have. So I first designed this on Adobe Illustrator, and then I cut out the design via a laser cutter or a CNC mill. And basically, I'm just etching out this on a piece of acrylic. And then, like I said before, this microfluidic chip consists of two pieces of acrylic with PDMS in between, and that PDMS acts as sort of a valve or a gate that kind of opens and closes based on whether there's vacuum pulling it down or not. So once I kind of assemble this, then I perform surface treatment with corona discharge, and essentially that means making the two surfaces, the acrylic and the PMS surfaces, more adhesive and creating more silicone oxygen bonds. And then finally, when I've treated both surfaces, I put everything together and I place it in an isotemp oven to allow the acrylic to soften a little bit, mold together, and everything to sandwich together. And so the result of everything coming together is this 3-output oscillator chip, which I've been working on. And this is based off of previous research done in Grover's lab. But essentially, this oscillator chip would be the main computer behind the IPC. It consists of a single vacuum input and then 3 outputs that would go to 3 level shifters, which I'll show you in a diagram at the end, which would then go to the compression sleeve. This microfluidic chip consists of 3 NOT gates. And so NOT gates essentially reverse or take the opposite of whatever your input is. If the input is on, then it would turn it off. If the input is off, it would turn it on. And this oscillator chip just works by taking in the vacuum and essentially turning on the valve that's adjacent to it, and then turning off the valve that's below it. And so essentially it's just a series of valves opening and closing. And when these valves, which are the white circles on the microfluidics chip, open and close, they basically allow vacuum to flow in, vacuum to flow out or out of the chip, and whatnot. And so we're able to open and close a bunch of valves and then create this sort of oscillation pattern. And so my testing setup, as you can see, is basically I have a compression sleeve, which is on my right-hand side, and I have the oscillator on the top. We have one vacuum line that is going to this oscillator, and out of the oscillator, there are 3 lines that are coming out, and these are essentially just creating oscillation patterns, which we could normally connect to a compression sleeve, but remember what I said, that vacuum isn't strong enough to inflate and deflate and create the patterns that we need for proper blood circulation. That is why I've developed these level shifters, which are pretty simple 3D printed devices, but they basically take in a pressure line, and that is split into 3. And I'm translating the logic of the vacuum into the pressure lines and taking that back into the compression sleeve. And so the low cost of this entire device is that it is essentially only taking one line of pressure and 1 line of vacuum. And it's basically just made of a microfluidic chip, a little bit of acrylic, PMS, and some 3D printed components. And then we're replicating all the functionalities of a regular IPC that it's built that is almost $2,000 and made of a lot of electromechanical hardware. And I've kind of covered this a little bit before, but further testing, I'm basically going to be testing the same exact setup that I have. And the compression sleeve runs on pressures of about 1 to 2 psi. And so that's what I'll be replicating. And I'll be using Arduino software to sort of log all those pressures and ensure that the oscillation patterns that are expected out of my microfluidics chip are present. I would like to acknowledge and thank everyone at Grover Lab, including Dr. Shane Hong and Dr. Grover, as well as Sam, everyone else in Grover Lab, and also UCR for giving me this mini grant to pursue this project. Thank you.